All right, so here we go. So this is to make up for the lecture I had to miss. Again, I apologize, but here's what we're going to do. We're going to talk a little bit about the course, a little bit about the next 7 days, and then we're going to get into matrices and matrix operations. It's going to be pretty short, but as far as the course goes, let me just give you this as a heads up. So next Tuesday is our exam. If you're in the Tuesday, Thursday, if you're in Monday, Wednesday, Friday, then your exam is Monday or Wednesday. It depends on your course syllabus. You can see the course syllabus for the Tuesday, Thursday. It's right here. Here we go. So several things to note. Number one, this information will not be on that exam. Okay, if you follow the syllabus and the scheduling that's on the syllabus, the information that will be on the first exam is everything from the first day, your course introduction, up until MATLAB introduction. Okay, we're going to do that the entire time, so the lecture directly preceding an exam will not be on the next exam. So that'll be the whole semester when I say the entire time. Next, I would like to tell you that for the My Engineering Lab homework that you're doing, you do have to do it by hand. So the Excel assignment, which was the first My Engineering Lab assignment, you did not have to do by hand, but now you have to do all of them by hand. So what's going to happen is Thursday after the exam, and I won't see you to talk to you until that Thursday, so you'll have to be prepared when you come in. But Thursday, after our first exam, which appears to be the 26th of September, you're going to have to bring in all of your My Engineering Lab work for the matrices assignment. That's this one, because there will be one on My Engineering Lab for this assignment, as well as for the trigonometry and geometry review. What will happen is I will say, okay, for the trig review, now I want you to turn in number 6, and you'll have 60 seconds to get that problem to the front of the room. And by the way, it won't be number 6, it'll be a number chosen purely at random. So you'll have 60 seconds to get that to the front of the room with your name on it, and then that's half of your grade for that homework assignment. We talked about this in the beginning of the semester. I just think a few of you may have forgotten. I'm giving you that extra time because, again, I explained in class I was being a little bit lenient based on people not having access to My Engineering Lab when they should have, even though you were given plenty of head start. So we're being a little bit lenient, but that is the last time we will do so with My Lab or My Engineering Lab. Second, the tolerance, no, that's not what I want to say. The performance. Okay, the reason we have you do all of this by hand, it's going to be 50% of your homework assignment, or I'm sorry, your grade, is the trigonometry and geometry review. So in Blackboard, you're going to see the My Engineering Lab or My Lab grade that you got for the trig review, as well as a handwritten, or a grade for your handwritten submission. So we have you write it all out by hand because what we saw historically is that if students didn't do their homework by hand, they had a 100 average on the homework and a 40 average on the exams. And that's not good for anybody because it doesn't set you up to be successful. You get upset with us. You don't feel that it's fair that, you know, the test covers things that we didn't do in the homework. When all actuality, or in all actuality, it does. It covers exactly what we covered in the homework. So that's that. The last thing is literally 60 seconds. When we give you the number, you're going to have 60 seconds to get it in, the end. Okay, so be ready. Bring all of your homework from the trig review. Bring all of your homework from the matrix and matrix operations. That's 7 days. Again, on Wednesday, I will send you an email to remind you, bring it to class. Okay, if you don't have it then, it's too late. Okay, we will not allow late submissions on handwritten homeworks. So with that being said, okay, the test is going to cover everything up to MATLAB introduction. Have your handwritten homework done 7 days from now, September 26th. Bring it into class. Let's get started with matrices and matrix operations. So in this course, we do several different phases. I explained that in the first lecture. One of them is math remediation, or at least getting you prepared with some of the skills you've learned in math for the physics, calculus, and engineering classes you're going to take in the future. Now, many of you have done things with systems of equations to solve for the unknowns. You've done methods like substitution, elimination, things like that. But we're going to teach you this semester a numerical method for solving for the unknowns in a system of linear equations, is what they're called, but a system of equations. To that end, we first have to have a conversation about matrices. Do a little bit of matrix algebra, get up to speed, and spin everybody up, and then all of a sudden we can, or I'm sorry, at that point we can get into Cramer's rule, which is the numerical method we're going to teach for solving systems of linear equations. So first, these are, let me see, here we go. So these are our learning objectives. We're going to define matrices and their applications in engineering. We're going to describe matrix dimensions and addressing. We're going to talk about a few mathematical operations using matrices, and then we'll summarize what a transpose is, and I'll explain to you how to use it. So what is a matrix? Roughly speaking, it's a rectangular organization of numbers. It's an abstraction, okay? It helps us solve equations. Now, you're going to see matrices in a minute, but a matrix is something where we have an array of numbers, and we can just reference a single value, all right? But in that array of numbers, it has several rows, several columns, or one row, several columns, or one column, several rows. We'll get to that in a minute. Every piece of information that is in a row together has something in common. And every piece of information that is in a column together has something in common. So it's a way of organizing a set of numbers into an array where we have all like elements in columns and all like elements in rows. And so we'll talk more about that when we get to Cramer's rule and systems of linear equations. But I've already used this term already. Matrices and arrays are somewhat of an interchangeable set of words in vernacular. So I may say array, I may say matrix, but in this class I mean the exact same thing. And then last, again, like I said, we have this large amount of information that can go into a matrix, but we just reference it as A or P or M. It's just the matrix that holds a tremendous amount of information. So when will you see matrices in engineering? Things like rigid body mechanics, optics, electromagnetism, statics, dynamics, linear equations, probability and statistics, and a lot of other classes. But generally speaking, as I've already said, and I'm going to continue to just reiterate this, a matrix is a nice, compact way of representing a large volume of information. So anytime you deal with a large amount of information, distilling it down to one object that you can reference makes things easier. Okay, it's a simplification in that regard. So we said a matrix is a rectangular organization of numbers. Looks like this. For the sake of this class, I didn't put it in the slideshow. I'm a little remiss. I guess I should have. We have common syntax that we hold to be true, and matrices are always going to be in brackets. So you see this is open bracket, little a, close bracket. And this is what a 3x3 matrix would look like. And I say 3x3 because, here's the thing. It has 1, 2, 3 rows, and 1, 2, 3 columns. So since it has 3 rows and 3 columns, we say it's 3 rows by 3 columns, or a 3x3 matrix, or more simply just 3x3. So predominantly we will just be using that 3x3 notation going forward. Well, here's what it would look like syntactically if we were to strip it away. I have a matrix A, so now I'm going to look at the indices or the addressing for the matrix. So A subscript 1, 1 is the element in A at row 1, column 1. Similarly, A subscript 1, 2 is the element in A at row 1, column 2, and then row 1, column 3. And then A subscript 2, 1 is the element in A at row 2, column 1. And then 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. Okay? But as is always the case, some people like referencing something in one way, some people like referencing it in another. So you will see similar notations, different notations to reference the same concepts. For instance, you'll notice that here we're using subscripts to denote the locations in the matrix A. However, some people like to use parentheses. It doesn't change the concept at all. It just changes the way that people are referencing the concept, and you'll have to be aware of that. The one that's a little bit stickier or trickier is this. This is actually more common in mathematics than any other field. But now, instead of a lowercase, and I'll go back, you'll see that over on the left-hand side, okay, we have a lowercase a equals, and then all of the indices or all of the elements in this matrix by index or location, they're also denoted using a lowercase a. But it is common in mathematics to find that we actually have the matrix by itself is uppercase A, and then when we reference elements in it, we use lowercase a. It can be a little bit confusing, but you'll just have to be aware of that moving forward. I also usually show and give you as a sort of cautionary tale, I show you that some people like to use indexes or indices, this A, open parentheses, 1, 1, close parentheses. Some people like to use an indexing scheme where there are no commas. Don't do that, ever. Like ever. Because you don't know if A11 is the 11th element in A or if it's the element in A at row 1, column 1. And to do you one better, you don't know if A1372 is the element in A at row 13, column 72, or row 137, column 2, or row 1, column 372. You just don't know. So use commas. They help break up information in the same way that parentheses, when using the order of operations, and we talked about earlier semester, it adds a level of specificity to things that just simplifies when someone is reading what it is that you have tried to communicate. All right, so now let's talk about a few types of matrices. First, there's a square matrix. Very easy. The number of rows equals the number of columns. This is what I've been showing you up to this point anyway. In this case, it's a 3 by 3, but it could be a 2 by 2, 4 by 4, 5 by 5, all the way up to an n by n. Next, a rectangular matrix. Very simple. The number of rows is not equal to the number of columns. This one is taller than wide. This one is wider than tall. Okay? So a tall or a wide matrix, as long as we don't have the same number of rows and columns, we're good. All right? A row vector. So I have routinely told you, or in several points this semester I've told you, that in engineering we like to use vectors a lot. So when we vectorize information, we can usually put it into an array or a matrix. It can come to you in a row form like this, or it can come to you in a column form like this. But the only point is that it has one dimension. Okay, so this one has one row, this one has one column. So if it only has one row, it has several columns. If it only has one column, it has several rows. But vectors can be denoted as a row vector or a column vector. And usually we don't call them row array or row matrix. It's usually just row vector. Just FYI. This is called an upper triangular matrix, where all of the numbers only exist in the upper triangle of the matrix. So there's a line called the diagonal that goes negative 21, 21, and 27 there. And so we have non-zero elements on that diagonal and everything above. That's an upper triangle. We also have a lower triangular matrix, which I didn't change. So let's skip that because I screwed that up. Sorry. Here's a diagonal matrix. For a diagonal matrix, we have only non-zero elements on the main diagonal and everything else is zero. We also have a special form of the diagonal matrix called the identity matrix. We'll talk more about this in our, again, systems of linear equations, or solving for the unknowns in a system of linear equations lecture. But in effect, the identity matrix is the matrix equivalent of multiplying by 1. Okay, we can multiply certain things to get there, or we can just understand that that is in and of itself like multiplying an array by 1. Okay, so now let's talk about matrix operations. Principally, there are two types. Number one, element-wise operations. Number two, non-element-wise operations. An element-wise operation is one where all of the matrices must be the same dimensions, because we're going to walk element by element through each one, down the rows, down the columns. So they have to have the same number of rows, and they have to have the same number of columns. One example of this is matrix addition. Also, matrix subtraction is the same. And then there are non-element-wise operations, where the two matrices need not be the same dimensions, and a good example of that is matrix multiplication. So let's walk very slowly through a matrix addition problem. So here we're going to take matrix A and matrix B, and we're going to add them together. Now, because they both have 2 rows and 2 columns, we know that we can. Okay, they have to be the same size. So we're going to use this syntax. We're going to say that A plus B equals C, where A more commonly has 4 locations, as we've talked about before. B has 4 locations, like we've talked about before. And so now we're just going to use those locations a little more abstractly to say that, look, C equals A plus B. So C at 1, 1 is going to equal A at 1, 1 plus B at 1, 1. This is why it's an element-wise operation. We're going to do element by element through these 2 arrays. And if we had different sizes of arrays, we would have elements hanging off that didn't have a partner. So here we go. So using these numbers only, we're going to say, all right, so I'm going to write my first matrix, 4, negative 3, 8, 9, plus 7, 9, 18, and 2. And what that equals is 4 plus 7 in the first position, negative 3 plus 9 in the second position, 8 plus 18 in the third position, and 9 plus negative 2 in the last position. So in effect, we get 11, 6, 26, and 7. Okay, so matrix addition is very easy. You just walk step by step, location by location, through each matrix, and you add up the partners, the companions. Subtraction is the same way, so we're not going to go through an example of that, except, you know, instead of add, you subtract. So good luck. So for matrix multiplication, let's talk about this, because some of you have done matrix multiplication before, and that's great, but there's a sort of logic to some of the indexing that becomes very, very useful in helping you complete the operation in a much more clear fashion. So we'll use matrix A and matrix B. Okay, so for matrix multiplication, I said it's not an element-wise operation, so there are some rules. All right, the first thing we have to do is we have to determine if we can even multiply these 2 matrices together. Well, to do that, and I'll show you in a minute, we're going to look at inner dimensions, and then the second step is we have to determine the dimensions of the product array, and for that, we have to look at the outer dimensions. So let's look at the dimensions of A and the dimensions of B. A is a 1 row by 3 column array. B is a 3 row by 2 column array. So again, for step 1, if the inner dimensions are equal, we can multiply. If they're not, then we can't, we just stop. Well, here, the inner dimensions are 3 and 3. So they are equal. So we can multiply. So now we move on to the second step. So the second step asks us, what are the dimensions of the product? For that, we focus on the outer dimensions, okay, 1 and 2. And we find that C, because it's A times B equals C, that C is going to have dimensions 1 by 2. So now let's take our two matrices. We know that this is our syntax. We know C is going to be a 1 by 2. Let's go ahead and get started. We're going to do, since we have 1 row, 2 columns, we're going to start at row 1, column 1. And we're going to say, okay, this is the element in C, our product array, the thing that we're going to multiply to get, at row 1, column 1. Except that that 1 tells us something else. It tells us that we need the first row of the first matrix. Now there are two firsts there, so this is the one that matters, that we need the first row. This column 1 tells us I need the first column of the second matrix in my multiplication. So I'm going to circle those two, my row of interest and my column of interest, and I'm going to focus on the values in those rows, or the row and column of interest. So here's how this works. This is called the summation of the piecewise multiplications. Okay, again, the summation of the piecewise multiplications. So we're going to focus on the first element in the row of interest and the first element in the column of interest. First element in the row is a -1. I'm going to multiply that by the first element in the column, 9. That's it. To that, I'm going to add the second element in my row of interest times the second element in my column of interest. So 5 times 21. And that's it. To that, I'm going to add the third element in my row of interest, 13, multiplied by the third element in my column of interest, -4. That's that one. As you can see, we now have the summation. We have 2 additions there, right? We're adding all of this up. The summation of the piecewise multiplications. Once I complete that math, we'll get rid of all of the formatting, we get that that equals 44. Now, because it's a 1 by 2 array, I have the element in row 1, column 1, but there's also a row 1, column 2, so now I'm going to focus on that. Again, that index for this element, row 1, column 2, tells me I need, again, the first row of the first matrix in my multiplication, A. The 2 tells me I need the second column of my second matrix, okay, in my multiplication, or B. So then I'm going to circle those again. And we're going to get started. Again, we're going to walk element by element, right? So first element in my row times the first element in my column. So -1 times 15 plus the second element in my row multiplied by the second element in my column, 5 times 0, plus the third element in my row, 13, multiplied by the third element in my column, 14, or, summing it all up, 167. Now I know that C is a 1 by 2, so we're just going to put those together. In row 1, column 1, we put our 44 that we computed, and in our row 1, column 2, we put 167. Now last, okay, a transpose. So for a matrix transpose, there's one thing that I think that it's very, very important that students know. More commonly, we put it this way, a raised to the t. When we meet in person, I'm going to show you a few more notations for this, but I'm recording this pretty late in the day, and I felt bad about it coming to you so late. So I left a few things out in order to just get it out in this time frame. So in class, we'll talk about a little bit more of it next Thursday. But this is the notation for a transpose. Sometimes you'll see it in the brackets. Sometimes you'll see it without the brackets. Okay, I told you in this class, for consistency, I like to keep the brackets. That means we're always dealing with a matrix, and not things like a determinant or a vector or an absolute value or a mean or things like that. So common notation just with the brackets. So look, a matrix transpose is a transformation of a matrix. It's not a rotation, and you're going to see what that means in a minute. But it's not like we're taking a matrix and just spinning it. Okay, it's actually different. If we were spinning it, it wouldn't end up with the transpose. It would end up with something else. But generally speaking, this is the way it works. I have an original matrix and I have its transpose. The first row in the original becomes the first column of the transpose. The first column in the original becomes the first row of the transpose. So original to transpose, right? Original to transpose. Original to transpose. It just works that way. The second row in the original becomes the second column in the transpose. The second column in the original becomes the second column in the transpose. We're going to put, again, I've got some numbers for you. We're going to play with this. It's going to make sense in a minute. But again, more abstractly, the nth row becomes the nth column, and the nth column becomes the nth row. Well, let's focus on the one we have. So the first row becomes the first column. So let's put brackets up. What we have is, our original is a 4 by 3. Our transpose will end up being a 3 by 4 because the first row becomes the first column. So 45, 28, 2 becomes the first column, 45, 28, 2. The first column, 45, 9, negative 24, and 85 becomes the first row. So there we go. Then we're just going to keep going, all right? So look, my second row becomes my second column. My third row becomes my third column. My fourth row becomes my fourth column. That's how you build a transpose. Now, why is this important? So let's say we have a vector. So I told you that there were times where we would denote a vector as a row and times where we would denote a vector as a column. I've also shown you that matrix multiplication depends on the matrix dimensions. So the inner dimensions have to match. So if someone gives me information as a row vector, but in calculation need it to be a column vector, then I can compute the transpose. If I have a whole bunch of row vectors, then following this principle, I can turn all those row vectors into an array of column vectors. Sorry. We're going to talk about how to do that more later this semester. At this point, I do apologize for it taking this long to get to you on Thursday, but then again, you have plenty to study for because the test is Tuesday. Best of luck on studying for the exam. And if you have any questions about this, please come by during office hours to ask, or wait until next Thursday after the exam, and then we'll bring it up in class. That way we can address it with everybody. So again, focus on the exam. I hope you had a good time at the job fair. Hope you got interviews. Hope some of you found an internship. You have several assignments out on Blackboard. Those of you in the distance class, all of your quizzes are now open. So good luck.